Linear regression has been around since the 1700s. It is one of the oldest and simplest ways to model a function. Now, you might be thinking, in this day and age, we have insanely powerful models available to us. I mean, who cares about linear regression? There are two camps of people that I've come across who have opinions on this. Those who believe linear regression is fundamental to anyone aspiring to be a data analyst or data scientist. It's kind of the ABCs of data modeling or modeling functions. And there are those who think it is a waste of time. Because of how far research has come in machine learning and statistics, you're better off spending your time learning about topics like deep learning or the more modern techniques. To be honest, I was part of the latter camp. My initial thought was, is linear regression even important anymore? I mean, who cares? We have XGBoost and Facebook Profit. So when I found out that linear regression was being used extensively by a client of mine in the insurance industry, basically to predict defaults on policy payments, I thought maybe there's more to linear regression than meets the eye. Hey folks, I'm Trent. I've been a professional data engineer for 6 years, and in this video, I wanted to explore linear regression for a few reasons. Firstly, I found that it was a great learning experience reviewing concepts like the R-squared coefficients and hypothesis testing with p-values and t-values. It was a great framing to learn this in linear regression, basically, or with linear regression in the background. It helped me understand the concepts more deeply. Secondly, it was really quick to work with and forced me to explore the data that I was working with in a bit more depth, as opposed to me just kind of taking the data and throwing it at the most complex or fancy model that I could find. And thirdly, the main advantage of linear regression and regression models more generally is that they are relatively easy to interpret. You can explain the parameters that the model gives back to you to make decisions. With those reasons in mind, I'll take you through some of the theory on linear regression. I think a lot of you have already got some exposure to linear regression, but fear not if you haven't. Then I'll move on to a practical application of LR to the AutoMPG dataset. It's one of those kind of classic datasets from the UCI machine learning repository. This is so that we can get our hands dirty and try this out for ourselves. So no matter your opinion on linear regression, I think it's valuable to explore and be exposed to at least once. And perhaps by the end of the video, you'll agree with me in saying that linear regression is more important than you originally thought. Or at the very least, you'll be more informed to be able to disagree with me on that. With all that in mind, let's start exploring. For this analysis, I'm going to be using Python, more specifically Python 3.13. And if you do want to follow along, I will leave a link to the repository in the description. In order for you to kind of match the setup and the packages that I'll be using throughout, you can go ahead and pip install -r requirements.txt. Whoops, not readme, requirements.txt. So all the requirements, all the packages that I'm using, I have listed them over here and their specific versions, so you can kind of match the setup that I'm using exactly. With that in mind, and with that setup complete, the first thing that I want to run through is the kind of theoretical basis for linear regression. I want to go through some theory so that we know what we're working with. This can be treated as kind of like a rehash of the theory if you've seen it already, but if you haven't before, this is just so that we're all on the same page when it comes to the model that we're using. For this part, I'm going to be using NumPy and Matplotlib, so pretty low level, or as low level as things get when you're dealing with Python. I'm just going to be using NumPy arrays basically to manipulate the data, so no fancy packages yet. I'll be using kind of sklearn and stats models later on when we actually do the kind of practical example, but for now I just want to do everything explicitly, and then Matplotlib for visualization. So let's go ahead and import that. So the first thing I want to go over is kind of the base theory for linear regression. So at its core, simple linear regression assumes that the data you're dealing with is generated by a process like the following. Y, some target variable that you're interested in, is equal to beta naught, some constant coefficient, plus beta 1, another coefficient, times x1. This is a predictor variable or input variable. So this is your independent variable and y is your dependent variable. So x is the data that you can measure and y is the data that you are kind of interpreting or targeting to use this model for or infer upon. And then lastly, there is this epsilon value, which is an error term. Now, this basically encapsulates kind of systematic error in the data generation process. So to explain that a little bit, it's kind of like if you were, let's say, measuring lengths. If you had a ruler, that ruler has some inherent error on it. If you were using the ruler, the 1 centimeter mark on it is probably not quite a centimeter. And so there is some inherent error in that measurement. And so in any process that you're dealing with, there's probably going to be some error or some noise, even in the data, the pure data that you get. And this is what the epsilon value is modeling, right? Now, I said that this was simple linear regression, and that's commonly used to refer to when we are using a single predictor variable or a single independent variable in our model. Now, just to explain this model a little more, this beta naught value is commonly referred to as the intercept. It's basically the value that y will take on when x is 0, right? So when x is 0, these terms disappear. This beta 1 x1 term disappears, and you're just left with an intercept term. Then this next coefficient over here kind of determines the slope of the curve that you're dealing with. So a high value, a high positive value over here will make a very steep straight line, and a very low value will make it flatter, and a negative value will make a line pointing downwards on your graph. So this is just a straight line model, basically. It is a pure line, if you were to chart this out. And we will go over that and picture this. All right, and below here is just a description of exactly what I said, just kind of more succinctly and less rambly, I guess. Cool, so let's actually visualize this. If I scroll down, I'm going to generate some synthetic data over here. The first thing that I'm doing is setting a seed value with a value of 42. This is just so that we get consistent randomness. This is just for kind of pseudo randomness when you're using a random package. So not super important, but nonetheless, it's good practice to set this. Then we're going to create our predictor variable, so our independent variable, with a kind of random choice over here out of a uniform distribution. So this will select random values between 0 and 10, and it will select 100 of them. Then we can generate some random noise over here, so our epsilon value, using np.random again, and draw this from a normal distribution. A normal distribution with mean 0, so average 0, and standard deviation 1. And we're drawing 100 points here to match our 100 x points, right? Now, this is important because basically, as part of linear regression, another assumption about epsilon, this error, is that it is a random error, right? And more specifically, it is a normally distributed random error. So this is an inherent assumption of linear regression that's important to note, that your errors in your dataset are assumed to be normally distributed and have a mean of 0. Now, standard deviation of 1, that's not necessarily the case. It's just that they should have a mean of 0 and it should be normally distributed, right? So this is an assumption about your data. And we're kind of manufacturing this data to meet this assumption. And then over here, y, the target variable, is equal to 2 times x. So this is beta 1 over here, this 2 value. So that represents the beta 1 value, plus 1, the intercept term. So an intercept of 1, or a beta naught value of 1. Plus the random error. So here is our value, or here is our target variable, right, being generated. So let's plot this out just on a matplotlib figure. So I'm just going to make a scatter plot of our population data over here with some labels on it. So let's go ahead and run this. And there we have it. This is our synthetic data where the exact equation is 2x plus 1 plus some error. And you can see this follows a straight line pattern. So it is a good candidate for linear regression. And well, of course it is, because we manufactured it to be. But this error is playing a role in kind of jiggling the points around. So off center, right? So they're coming off of this line. Now, something that I am going to refer back to is kind of a true regression line. So our inherent assumption is that the data generating process has a true straight line. And when I say true straight line, it is this part of the equation over here, this 2x plus 1. This is the true regression line, or the real regression line, right? And then, accepting some error on top of that. So really, what we want to estimate with linear regression is the true regression line over here, accepting the fact that we are going to get some errors. And I will touch on that as we get through the theory. But nonetheless, this is the type of data that is a good candidate for us to model using linear regression. So the model that we produce is something like this. We take a y hat, a predicted variable, is equal to beta naught plus beta 1 times x. Now, technically speaking, this beta naught and this beta 1 should get a hat. The hat represents kind of predicted or estimated values. Typically in statistics, right, you give something a hat when you are estimating it. So these don't have a hat on them out of pure laziness or syntactical error, but these are estimates of beta naught, and I've used kind of lowercase values here, lowercase y with a hat on it, lowercase x over here, to represent that we are going to be estimating the y value using the input x values. And you can see here, this is our estimate of the regression line. So what we're trying to estimate is this part of the equation over here. So how do we use this model? How do we get to good estimates of beta naught and beta 1? That's truly what we are estimating in this case, right? These two coefficient values. So the value that linear regression aims to minimize is the residual sum of squares. And the residual sum of squares value is the difference between your y hat predicted values and each of the true yi values that you know, and then taking the sum of squares of those values. So it's kind of the distance between your predicted y value and the known y values, right? You're trying to minimize that so you get as close as possible to the true y value. And it turns out, basically, and in a very hand-wavy way, like super hand-wavy, these are the values that minimize the residual sum of squares for beta 1 and beta naught. And over here, I actually remembered to add the hat values. So these are the equations you get. Now you can derive these from scratch. Basically, you would take the residual sum of squares and do the kind of typical minimization or finding of extrema values that you would see in any introductory calculus class. Basically, take the first derivative of this and set it to 0, right? Or find where the first derivative is equal to 0, and find the second derivative, or where the second derivative is positive, right? So greater than 0. And that is pretty easy to see where this would be, because this is a parabola, right? So this is a squared term, so it kind of makes a smiley face graph, right? And the minima that you're looking for is right at the bottom of that, and it turns out to be these values over here when you use beta 1 and beta naught. I will leave the exact derivation of this as a exercise to the viewer, if you're that way inclined, right? Now, in real life, we typically don't have the full population of the data that we are modeling, right? We don't get the kind of full population of the data. Instead, you get a subset. Now, in our case, of course, we have the full population because, well, we manufactured it or generated the data. However, to simulate real life, right, I'm going to take a sample set of indices over here. So I'm just going to choose 50 random indices, so about half of our data, and use that as part of an X sample and Y sample over here. Then, using the sample of data, I am then going to use the equations for beta 1 and beta naught. So I've just typed these out explicitly using basically just NumPy, right, to type out those equations over here. Then I'm creating an X domain over here so that we have the kind of full domain of X values, right? We're generating 100 points over here between 0 and 10. And then creating a predicted value so that we get a nice regression line. So here is our y hat, and this is equal to X domain times our beta 1 estimate plus beta naught. That is our model. Then I'm calculating this y hat known over here. So basically taking our X sample, so our known data points, and getting an estimate for those so that I can calculate the residuals, right? So this is basically measuring the y values that we actually already know versus what our model predicts those y values to be. And that's how we find a residual value over here. We take our y sample and subtract our y hat known value over here to get residuals, the difference between our prediction and what the value truly is. Right, so this is pretty typical of like supervised machine learning, right? You have known examples, and now we're gauging how well we've done. And these residuals are just measuring the gap between what is the true value versus what our model predicted. All right, and then I'm just plotting this out again, so on a figure over here, but instead this time I'm also plotting the regression line that we calculated, so our regression line across the domain. and then plotting out the residual values. So plotting out these residuals just to show you them visually on the actual plot with some black dashed lines, and then adding labels of X and Y to this. So, and then just labeling the graph. So let's print this out and see what it looks like. Okay, and what this gives us is our regression line, the residuals, and our population data. So this is what our model looks like, this red line over here. Actually, let me make this a little smaller, a little bit smaller. Awesome. So this is our actual model over here, which is the red line going in and amongst our actual data over here. So it is minimizing that residual value between the data points that we know. And we can see the data points that we know because we've got the black dotted lines on them illustrating the residual values over here. Now, interestingly, what would happen if we just kind of made our sample a lot smaller? Let's say we only got 2 data points over here. So if I ran this, right, our model isn't actually doing too badly just because of how well manufactured our data is. But maybe if I do this a few times, so after running this a couple of times, you can see that the regression line is kind of getting worse. So if we picked 2 random data points, we are more likely to kind of miss the true regression line, right? Okay, let's set this back to 50 and rerun. All right, I just wanted to kind of show the thing about sampling, right? Like if we got a really small sample, and we got different samples each time, the regression line or our predicted regression line would move around. All right, so let's actually print out our beta 0 and beta 1 estimates over here. And beta 0 is 1.14, or estimated to be about 1.14, which is pretty close because the true beta 0 value is just 1. And then beta 1, which has a value of 2, is 1.96, or actually 1.97. So pretty damn close to 2, right? So our estimates are quite good. Again, this is manufactured data, so of course the estimates are going to be good. Now, something interesting, however, is that even if we did know the perfect coefficient, so if I got this perfect and got a 1 and a 2 over here, so we got our coefficients perfectly, we'd still have an error term, right? We'd still have error in our data because our data inherently has error, right? That's what we were discussing in the beginning with that epsilon term. So the residual sum of squares is technically an estimate of the true error term. Hey folks, it's Editing Trent over here. While I was editing the video, I noticed that I said something incorrectly, or I phrased something incorrectly in the theory section over here. Effectively, I was saying that the RSS, or residual sum of squares, is a estimate of the true error term epsilon. Now, that's not technically true, right? Because RSS is an aggregate of all the residuals we have. So the correct way of phrasing this is that the residuals that we get, the residuals from our model, are an estimate of the true error terms. So the idea here is that rather than the residual sum of squares, the whole aggregate being able to be substituted for epsilon, it is actually the individual residuals associated with each data point that are the estimate. So I hope that doesn't cause too much confusion. I was just noting that effectively we are estimating the error by doing this residuals thing, but I didn't want to cause any confusion or kind of like misinform you. I just made a mistake there. Anyway, I hope that doesn't take away from the video too much. Thank you so much, and let's get back to the video. I just thought that this was interesting because I remember minimizing residual sum of squares. So when I first learned about linear regression, learning about the minimization of residual sum of squares, but I never thought about it in the sense that the residual sum of squares is actually an estimate, for epsilon, right? So again, if we knew the perfect values for beta 0 and beta 1, we would still have some error on it, right? And that is modeled by the residual sum of squares. So let's print out our residual sum of squares value over here. So let's go ahead and do that. And we can see that this is 39.9, or about 40 y units squared. Now, if we use something like the residual standard error, right? So this is the kind of meta error, the standard error in the residual sum of squares, because as I said, RSS is technically an estimator itself, so there is some error associated with it. So it's kind of a meta error, the error in our estimate for the actual error, right? The residual standard error basically estimates how much our regression line deviates from the true regression line, right? So the true regression line is 2x plus 1, and our estimated regression line is 1.97x plus 1.14, right? So the residual standard error is a gauge of how far we're missing the true regression line, and also happens to be the standard error associated with the residual sum of squares. Now, the important thing to note about residual standard error over here is its proportionality, right? So if we intuit how this looks, basically, if we take this n term at the bottom, if we get more data points, that's what n represents, how many data points we have. If we get more data points, our standard error gets smaller. So with more data, we get less standard error, right? And if the residual sum of squares is bigger, of course, this is going to get larger. So that's the proportionality. More data is better, it shrinks the error. Residual sum of squares will expand the error. Now, this -2 term over here is an artifact, a mathematical artifact. What I mean by that is this just pops out because we are using estimators. If you've ever done any kind of introductory stats course and you've had to come up with an unbiased estimator for something like variance, you will note a kind of -1 term appearing in that estimator, and that's just to unbias the estimator. So this is a similar kind of thing over here, or a similar idea over here. This just pops out due to us using estimators. All right, and as before, with residual sum of squares, let's calculate our residual standard error over here by hand or by NumPy. Okay, and then this is 0.9, right, or 0.91. This means that on average, we will deviate from the true regression line with our model by about 1 y unit, Now, whether or not that is good depends on the problem context, right? So if you're dealing in, let's say we were estimating dollars, y represented dollars, if you were deviating by $1 on average, that might be acceptable. But if y was millions of dollars, right, that may not be so acceptable to deviate by $1 million on average per point that you predict. So the residual standard error is great to judge the error in our model, but as we were going through there, like the difference between the units, it's quoted in the units of the y variable. So it's hard to judge how big is too big when it comes to the standard error or residual standard error. What would be great is if we had a more definitive and easy to interpret measure. And this is where the r-squared statistic comes in. So r squared is equal to the total sum of squares, and we'll go through what that is in a second, minus the residual sum of squares divided by the total sum of squares. So the TSS value over here, or total sum of squares, is actually a measure of variance in the data before we've done any modeling on it. So it measures the total variance in y before you've done any type of regression on it. And it's basically how much variance exists in the target variable before anyone has done anything to the data. So what we're really measuring over here is the variance minus the deviation of our model from the data, RSS, divided by the total variance. So effectively, r squared is the total proportion of the variance that can be explained by our model, right? So we've got the total variance, and the total, and what this is a proportionality between how much of the variance we explained with our residual sum of squares. So if r squared is equal to 0, that means none of the variance is explained by the regression, right? But if r squared is 1, it means all of the variance can be explained by the regression. Basically, if it was 1, it means that your residual sum of squares is 0, i.e. you perfectly nailed every single data point, right? So what I'm getting to is that r squared is helpful to judge how well your model fits the data, but the thing is, if you get an r squared of 1, that's a bit suspicious, right? You're probably overfitting the data. No ways have you gotten a perfect residual sum of squares value that matches your total variance in the data. Further, a r squared value of 0 is also suspicious, right? Because if you have just random noise, there should always be a little bit of correlation with your data. Even if it's completely random, completely unrelated, you'll always be able to find a little bit of like covariance in the data. Anyway, the main point that I wanted to get to is that when I thought about r squared before reviewing this content, all I could remember was that 0 is bad, 1 is good, right? But I hadn't really thought about what does it mean in a long time? Like, how do you get to this r squared value? Like, what is the underlying equation? And like, I mean, who cares about it? So it was really cool to go over this and remind myself that r squared is the total proportion of the variance explained by your model, in this case, linear regression. So let's go ahead and calculate our r squared value. And we can see it's like 0.98 over here, which means 98% of the variance in our data can be explained by our model. That 2% can be attributed to the randomness in the data itself when we drew the error from a normal distribution, right? But this is super good, super close. If we got this score in real life, I'd be pretty damn suspicious of the model. Yeah, of course, this is doing well. Again, using manufactured data that's perfect for linear regression. Okay, so up until this point, we have been dealing with simple linear regression in the sense that we had a single predictor variable. But what about if we have many predictor variables? Like, oftentimes in your data, you don't just have one kind of independent variable. You probably get many independent variables to predict some target. And that's where multiple linear regression comes in. So it's an extension of simple linear regression by simply adding more predictor variables. So now we assume that our data is generated by a process like the following. Y equals beta naught again, so an intercept value, plus beta 1 x1, so up until this point, this is basically simple linear regression. But then we add new terms like beta 2 x2 plus etc. until we get to beta p times xp. And then still some error or an epsilon term to capture systematic error in our data. So the model we are using is no longer kind of a straight line, right? It's not technically a regression line, but rather a regression plane in p dimensions, and I will illustrate that in a few. But what I wanted to touch on is that we now estimate the regression coefficient vector beta, so many values of beta over here, from beta naught all the way up to beta p, using the normal equation. So this is pretty typical, or you'd come across this in like an intro to linear algebra course. This equation is so common that it gets its own special name, the normal equation. And just kind of looking at it at a high level, it's basically the inverse of x squared, your x matrix squared. And at the top, you have x transpose times y, or x times y, right? So this estimates your beta values. And in this case, X is called the design matrix. This contains all your predictor variables plus a column of ones for the intercept. I'll explain that in a bit more detail. But for now, I just wanted to go over that Y is still the target variable vector. Beta is the coefficient vector, this is what we aim to compute. So our multiple linear regression with two predictors, for example, if we were to just use two predictor variables, so an x1 and x2, this is what your design matrix would look like. You'd have a column of ones, and this is to deal with the beta naught value right over here. So you want to calculate beta naught, and basically its coefficient, or its multiplier in this case, is not a variable. Instead, it's just the value 1 because it is an intercept, and that's why you have to add this column of ones. And then you have your columns of data over here, so x1 and x2 over here, and then all the elements of x1 and x2. And you can simplify your equation over here by just y equals beta x plus epsilon. So this equation looks a lot simpler. Of course, there's a lot of nuance hiding underneath here because, in linear algebra, that's always the case. There's always like some weird nuance in it. But this is what the setup would be like in multiple dimensions here. And yeah, this just explains again what I said more succinctly. So let's actually visualize this. So let's see what a regression plane looks like when we have two predictor variables and, plus an intercept over here. And to do that, I'm going to generate some random data again. In this case, I'm going to use Qt. So I've got that in my requirements over here, but this is just so that we get a nice 3D plot that we can actually rotate. So this is just there so that we get an easy to use plot. No other reason why I'm doing this kind of percentage sign matplotlib Qt over here. That's just so that it uses the Qt library rather than printing out the diagram in line in the notebook. All right, and then I just generate some random data from uniform distributions. Again, x1 and x2, I generate them independently of one another, and then create our epsilon value here. So drawing that from a normal distribution, also adding some extra standard deviation to this just so that it's clear that the points are off the plane, just to make the visual nice. and then creating our target variable over here, y equals 1 plus 2x1 plus 3x2. So our extra coefficient here is 3, so just adding that in, plus our error epsilon, right? And then setting up x in a nice format so that it matches this format over here. So we've got a column of ones and then our predictor variables next door to one another over there. Then we can get beta hat over here using the NumPy linear algebra method or package over here, sub-package, to take the inverse of x transpose and x. And then on the numerator, we have x transpose times y, right? So I was calculating this by hand, and it reminded me of the first time I did this, back when I was learning about linear regression. I was using MATLAB, and it reminded me that I never want to use MATLAB ever again, right? So anyway, this is the beta hat vector. So I just wanted to extract those values so we can print them out. Then getting our y predicted over here. And this is just some plotting code over here. So getting our observed data and then plotting out our plane on a mesh grid, right? Or plotting out our data on a mesh grid of x1 and x2. So that's kind of the two bottom axes, and then having a y grid over here as well. So we can plot this out as a surface in 3 dimensions and then just label it. So let's actually run this and take a look. Okay, and our output looks like this. So let's actually zoom into that. And there is our regression plane in 3 dimensions, right? So the plane itself has 2 dimensions. It's a 2-dimensional object in 3-dimensional space. And if I move this around, right, you can see that our data points are kind of just off of this plane. So as many above as there are below, right? Because we are performing a regression and we're fitting this plane in between all the data. And yeah, once again, I used Qt so that I could do cool stuff like this and rotate our graph around so that we could get a better visual of what this looks like. Okay, before I get too distracted by that, let me close this and just say that the definitions for things like residual sum of squares, the residual standard error, total sum of squares, and R squared kind of extend naturally to the multiple linear regression case, right? They extend as you'd expect, basically extra terms in the calculations. Now, one remark that I will make is that R squared in the simple linear regression case happens to be the same as covariance. So if you've ever dealt with covariance before, R squared and covariance are the same thing in simple linear regression when you're dealing with a single predictor. But in multiple linear regression, R squared stops being the same thing as covariance. Covariance actually becomes a little more complicated in the multi-dimensional case. But I just wanted to make that remark. I thought it was kind of cool that they're equivalent in the simple linear regression case, but they are not equivalent in the multiple linear regression case. All right, so we have gotten through some theory and have a good basis to work with this model. So to work with simple linear regression and multiple linear regression, let's do exactly that and use some real data so that we can face some real problems instead of kind of just going with the kind of nicely fitted synthetic data where everything looks nice. So let's get our hands dirty and try this out on some real data. Okay, moving on to some more practical linear regression, i.e. using linear regression on a real data set. The data set that we're going to use is the automobile miles per gallon, or AutoMPG dataset. So this was originally published as part of the StatLib library, and the data that I sourced, or the data as sourced from the UCI ML library, is in the .data format. So it's a fixed width format bit of data. So yeah, it's pretty old, right? And it has no columnar metadata. We'll go through how to deal with that. And also the UCI source doesn't provide the original units of the data. So I needed to kind of guess those, or kind of take a good approximation as to what the unit should be for each of the columns. And why I did this is because, well, I don't know if you can tell by looking at me, but I'm not really what you'd call a car guy. So I had no idea what any of this meant. For example, what the heck is a displacement? No idea. So I went and looked that up and then also inferred what the actual unit should be. So I assume that these were imperial units. Now I am South African, so I deal with the metric scale. So I think in kilometers and degrees Celsius, not so much miles and Fahrenheit, right? But we deal with what we get, right? So just to go through each of the variables quickly, the displacement is the engine displacement. So it's how much cylinder volume is swept by the pistons in the engine. So this excludes the combustion chambers. It's just how much space the pistons use. And this is measured in cubic inches in imperial. Miles per gallon is how many miles a vehicle can travel on 1 gallon of fuel, assuming that there's no load in the vehicle. And this dataset quotes city cycle miles per gallon, which is a measure for driving in urban areas. So as opposed to driving on like a single straight road, this has got a lot of stop-start in it, right? So a lot of stop-starting of the vehicle. And this is measured, of course, in miles per gallon. Then the cylinders is how many cylinders there are in the vehicle's engine. So cylinders comprise of a piston and 2 valves. Yes, I needed to get to this level of detail because I had no idea what this meant. And they are located within the engine. And this is just an integer value. It's the integer number of cylinders in the engine. Then horsepower is the unit of measurement of power, or the rate at which work is done. So this is usually in reference to the output of an engine or motor, exactly what we're dealing with. Now, interestingly, there are multiple different types of horsepower. There's kind of metric horsepower, and I assume they're quoting imperial horsepower over here. So there's HP imperial and HP metric. And there is also, wattage. Sometimes engine power can be measured in watts, but anyway, I assume that this is in horsepower imperial units. Then the weight is the relative mass of the vehicle, so it's how many pounds it weighs. The acceleration is the time taken for a vehicle to cover a quarter of a mile from an idle state. So from it being completely stopped to how many seconds it takes for it to cover a quarter of a mile. There are also different ways to measure acceleration, but from looking at the data and looking at some of the stats externally, like looking up different car values, it seems that this is the quarter mile acceleration being quoted in this data set. And then the model year over here is the year in which the vehicle was produced, right? The model of that vehicle was produced. Now, this covers vehicles from the 1970s and 80s, so kind of old school cars. But yeah, this was just to note what the model year was. And the origin, I have no idea what this is. So this could be the origin of the vehicle, but I really don't know what an origin of 1 means. So this is an integer value in the data set. I have no idea what this could mean. So if anyone does know, let me know in the comments. But for now, I'm just going to ignore this for the analysis. Okay, great. Let's take a look at the actual data itself. And as I mentioned, this is in fixed width format, so each element in the data is separated by a set number of spaces. In this case, it looks like 3 spaces, and there's the element. And they are using quotation marks or double quotes, right, to show the sanitized string data. By that, I mean that these spaces will not be interpreted as element separators in the data. Instead, this is the element itself. So the quotes just kind of protect us against interpreting these spaces as separators in the data. That's what I mean by sanitization. Now, as I said, there's no metadata in here, so we need to know the order of the column names, how they are quoted, in order for us to know which column is which, basically. So in this data set, there is no reference to the column names. So we have to depend on this auto-mpg.names file over here. And this quotes the names of the attributes over here and tells us the order in which they appear. So we have to depend on this in order to get our data in a good format. This does contain some other information about it. Unfortunately, it doesn't tell us that the description of the attributes. It just kind of tells us, these are multi-valued or continuous, discrete or continuous, or it's a string. Yeah, it doesn't tell us the actual units. This is also where I found this was city cycle fuel consumption, right, or fuel economy. All right, let's get going on some analysis. So opening up the notebook over here called autompganalysis.ipynb. In this notebook, I just have some imports over here. So I've just imported all the packages and kind of functions that we're going to be using from various places. So places like pandas, numpy, stats models, sklearn, matplotlib, and seaborn. We will use each of these and it will become apparent where they are used as we go through. But for now, I'm just importing these so I don't have to kind of keep jumping back and forth to import them. And I like to keep my imports at the top of my notebook. So let's go ahead and run this. All right, with the imports done, let's go ahead and read in our data into a pandas data frame. So let's call it df for data frame. and we need to do a pd.read underscore fixed width format, or FWF. So that's the kind of data that we're dealing with. Let's go ahead and give it the path over here to our data. So I've put this in a place called data, and under that it is auto-mpg over here. And now we need to specify the column names as well. So let's go ahead and add that as an argument over here. So we can add names equals, and we will just add the column names in the exact order in which they appear. And there we go. I've added the names in the order that they appear in the .names file over here. All right, so let's just print out the first few values of this using a df.head. And there we have it. We have successfully read in our data from the fixed width format file. Let's go and look at some high-level stats on our data. So the first thing I want to do is add a df.info over here. So df.info, just to take a look at the data types and how many null values we have. So it looks like we have 398 entries, so a pretty small amount of data. And we have 9 columns over here, so all 9 columns. Looks like we don't have any nulls, and the data types look okay, except for horsepower, right? So horsepower is an object, and I wouldn't expect that. That is a numeric value or a number over here. So these should be interpreted as numbers, but it is interpreting it as a object. So we'll have to inspect that and clean that up if necessary. All right, but let's look at some high-level statistics on our data. So let's do a df.describe to look at our numeric values. And all we're looking for is if there's any like anomalies in the data, like miles per gallon should never be negative. Like, are there any negative values? What's its average? Is the maximum reasonable? So just kind of scanning through and taking a look at the data, get an idea of what's contained in here. So it looks like the minimum miles per gallon, or the smallest like miles per gallon you get, are 9 miles, which is a super expensive car to own, right? And the maximum is 46.6. Then in terms of things like cylinders and displacement, this looks reasonable. The maximum is 8 cylinders, so 8-cylinder vehicles. Engine displacement, yeah, no negatives or anything like that. That looks reasonable. For weight, this looks reasonable, but the maximum is 5,140, so like 5,000 pounds. And again, I don't really think in pounds, so it's hard for me to visualize how big that is, but 5,000 sounds pretty heavy to me, so pretty big car, right? Especially when you look at the minimum, which is like 1,600 over here, so 1,600 pounds. And the rest of these look reasonable as well. Now I'm interested, of course we don't have horsepower showing up. I'm interested to take a look at that. So let's do a df.describe again. Describe, but let us include O for object. So now this will do a describe on our object-like column. So let's run that. And we get our horsepower and car name. So it looks like there are 94 unique horsepowers in here. And the top one is 150. This occurs 22 times. That's the most frequently occurring horsepower that we have. And then in cars, it looks like the unique number of cars we have is 305 versus 398 records. Now, this just makes me want to check for duplicates, right? To make sure that we don't have any duplication in the data itself. And then, of course, we need to figure out why is horsepower coming through as an object, not as a number. So let's explore that. So let's deal with the horsepower problem first. Let's take a look at the data. Take df, and more specifically df horsepower. And now I want to search for places where the horsepower is not a number, right? So it doesn't contain numeric values in it. It contains something else. So to do that, I'm going to use a regex or regex expression to look for places where it is not numeric. So to do that, let's take .string. So to access the kind of string modifiers in pandas, .string contains, in this case, and we will use raw string R, and we will specify 0 through 9 and a dot. So the decimal specifier, or the period over here, is to specify decimal, so that is acceptable as well. Now I want to see where it is not 0 through 9 and not a dot, or not a dot. So to do that, I want to negate this expression and say not 0 through 9 by using the caret symbol over here. So let's specify here that we are using regex, so regex equals true. And that should be good. Yeah, so let's take a look at all the places where horsepower is not a number. Okay, and printing that out, we get 6 values back, and it looks like these are question marks, and that is why it was being interpreted as a object type or a string rather than a number. So to rectify this, we just need to go and replace these question marks with like np.nan or something like that. So a true null value or a null value that can be used in a numeric column. All right, let's take a look at our duplication as well. So I'm going to go ahead and add a line over here to make sure we aren't getting duplicates in the data. So let's take df and let's do df.duplicated. So this will just return true if we have 2 lines or 2 complete records that are the exact same. So this filters to see if we have duplicates. If we have none, this should return an empty data frame. Let's run that. And yeah, this is empty. So there are no perfect duplicates in the data, but let's look at the Ford Pinto example. So let's take car name over here. Car name equals Ford Pinto. And when I looked at the values over here, you can see actually these have quotes in it. So it should actually be Ford Pinto. And that's another thing we have to clean. We have to get rid of these double quotes in the car name. So for now, though, I need to actually specify those quotes. So I'm going to use an escape character, so \quote, so that we interpret this as the double quote character rather than it being interpreted as a Python string, because double quotes mean string in Python. But if we use \double quote, it is the true or the raw double quote character. So over here, I can do that. Awesome. So where the car name is a Ford Pinto. Let's run that. Okay, it looks like we have 6 different Ford Pintos over here. And if we take a look at the data, it seems like the model year is different across the board, except for these that are from 1975. So both these Ford Pintos are from 1975, but it looks like the data differs. And that's why they didn't show up as duplicates, right? Because their actual data, their acceleration times, their weight, yeah, everything's different over here. And most notably, their cylinders are different. So this is a 4-cylinder Ford Pinto, and this is a 6-cylinder Ford Pinto. So it's probably the same car or same car model from 1975, just 2 different variants of it. One has 4 cylinders, the other one has 6 cylinders. And so the kind of weight and all the other statistics are different, right? So I'm pretty happy that we don't have duplicates in here. Just something to note that we can have the same kind of car name across different years. And then even within a year, we can have the same car appearing multiple times, but perhaps it's a different series of the car, or we can assume it's a different series of the car. All right, let's move on to actually cleaning up the problems that we have found. So horsepower, the quotes in the car names, all of that kind of stuff. All right, to do that, let's create a new data frame called cleaned df and make that a copy of the original data frame. And then take cleaned df over here and take horsepower. What we want to do with horsepower is replace those question marks with nan values. So to do that, I'm going to say clean df horsepower over here dot replace any question mark character with a numpy.nan value, so a null value, a numeric null value, right? And then we need to convert horsepower from an object type to a numeric type. So let's go ahead and do that. Yeah, horsepower is equal to pd.toNumeric, and we want to convert horsepower again. And we'll say errors equals coerce over here. So this coerce basically means if we come across any other example, so besides, the question mark case or anything like that, we will just kind of replace those with a nan as well. So that's what errors coerce means. I suppose we could have actually just run this line, perhaps. But it's better to just kind of handle the cases we know about explicitly so that it has predictable behavior. But that's what errors coerce does. This is kind of a lazy way of doing things, but I'm not too worried about it because there is such a small amount of data. We would notice if there is any other influence on horsepower that affects it, right? So I'm okay with this. Let's just check that this compiles, right? So cleaned df over here, clean df.head, and printing that out, that compiles fine. Awesome. Let's also handle these quotation marks. So clean df car name in this case is equal to cleaned df car name dot string this time. So now I can't use a full replace. This replace method will replace an entire element, whereas I want to replace a part of a string. I don't want to replace the entire string over here. So to do that, I'm going to say string dot replace, and I want to replace quotation marks. So again, I'm going to have to use an escape character here. So escape double quotes, and replace that with the null or empty string. All right, great. Let's just print out our data frame again. Oops. So printing that out, make sure that this compiles nicely. All right, so that compiled all right. And over here, we have our car name. It has got no quotes in it, and it seems like horsepower is fine, like it's being interpreted as a number. Just to validate that, let's just take cleaned df.info, run that. And horsepower is now a float64 type, and it has 6 null values, which is exactly what we found. So this is working as expected. Okay, let us actually visualize some of the relationships in and amongst our variables. Now, what I want to do is preface that by saying that I'm going to use horsepower as our target variable. So I'm going to be modeling horsepower. Now, typically in this data set, it's actually miles per gallon that gets modeled, right? So you predict miles per gallon based on all the other factors in the data, but I'm going to go ahead and use horsepower. And why is because we have the missing values in horsepower. So I'm genuinely interested to see if we can predict some good horsepower values. So with that in mind, and with the fact that we are going to be using horsepower as a target, let's plot each of our variables against the horsepower value. Okay, so let's take our numeric columns. So I don't want to plot any of our string values, so basically just car name against horsepower. I actually just want the numeric column. So to do that, I will take cleandf dot select dtypes over here and say include number types. Yeah, include number. Awesome. And take the dot columns value from there. So this will give us all our numeric columns, or a list of our numeric columns. And let's go through each of these. So for col in numeric columns, so looping through each, and then saying if column does not equal horsepower, then let us plot against horsepower. Take the column value and plot it against the horsepower. So I'm just going to add some plotting code to this so that we plot a scatter plot for each of these. Okay, so with some plotting code over here, so create a figure, then go ahead and plot the X and Y values, add some labels to this, and add titles to each of them so we know what we are plotting against horsepower. Ooh, type error. So let's actually use the seaborn scatter over here. I think I was mistakenly using the matplotlib one. So let's take a seaborn scatter plot with X and Y in it. Yeah, all right. That comes out nicer. Awesome. So looking at this, we get each of our variables plotted against horsepower, just a basic scatter plot. And horsepower versus miles per gallon over here. This follows a kind of downward trend over here. Not quite linear, but linear enough. You could fit a straight line to that. And this basically means that as we increase miles per gallons, or as the fuel economy increases, so the horsepower decreases. And that kind of makes intuitive sense because the fuel economy or better fuel economy cars are generally less powerful. Then looking at cylinders. So cylinders is a discrete value, which is why we have all this bunched up data over here, right? So this has got a small amount. It's like got a small amount of discrete values versus horsepower, right? And if we plotted a straight line here, we would get some error, like quite a bit of error, because our straight line would only give us one value per kind of like cylinder set over here. But that's okay. Like we would get quite a bit of error, but that's okay for now. You could still fit a straight line to this, and the general trend we can kind of see is as you add more cylinders, so the horsepower increases. Then looking at engine displacement versus horsepower, also kind of linear. There is a bit of bunching of data going on in the lower values over here. So you could put a straight line through this and kind of say that as displacement increases, so the horsepower increases as well. Then we move on to weight. So as the mass of the car increases, or as the weight increases in pounds, so the horsepower increases, also pretty linear. Then acceleration. Now this decreases because as your horsepower is bigger, or bigger horsepower values are there, so the acceleration time is lower. Basically, it takes less time for a car with more horsepower to cover a quarter mile. So that's why this is kind of negatively correlated over here. Or you could have like a downwards facing straight line plotting through these values. Then looking at the year versus horsepower, this looks kind of randomly scattered, and year is pretty discrete, right? We have, from 1970 to 1982. This looks pretty randomly scattered. I don't think there is much of a relationship between the year and horsepower, but nonetheless, there it is. And at least we can kind of see the distribution over here. There isn't like a definite trend when it comes to horsepower and year of the vehicle. And then origin, yeah, I'm just going to completely ignore this. The origin values are 1, 2, and 3, and I have no idea what any of that means. Okay, let's do some actual simple linear regression here. And the first thing I'm going to start with is an inferential question. Now, there's a subtle difference between kind of inference versus prediction. Inference is what you do to kind of like describe the relationships between the data that you already know, whereas prediction is more of like the sexy stuff, right, in data science, or the more typical kind of use case that we hear about. It's where you're predicting unknown values. So the first thing you want to do is understand the relationships between the variables that you're working with, and this is inference, and then move on to kind of like predictive type stuff. And that's exactly what we'll do. I just wanted to emphasize the difference here, that we are going to start with an inferential analysis with the data that we know, and then later on we will do some predictive work using linear regression in both cases. All right, but starting off with simple linear regression, let's look at how miles per gallon affects horsepower. So simple linear regression, again, we're just going to use a single predictor. In this case, it is miles per gallon. All right, and the setup for this is going to be using stats models. So I'm going to use stats models for the inferential part. It's just kind of easier to use, and it gives us a bit more information on the inference side rather than the kind of sci-kit learn library. So stats models is useful for this kind of analysis. All right, and to set things up, let's create a variable called xvars, and this will be the matrix of our x values. So in this case, we're just going to have 1 miles per gallon, but later on we'll use a similar setup when we look at multiple linear regression. We'll just add more variables to this. So let's take clean df over here and select, in this case, I'm going to select just miles per gallon. So I'm using double square brackets here to make this a data frame type. So xvars is a data frame. It just happens to have a single column. But now when I set up yvar, this is just going to be a single value. So clean df. And in our case, this is horsepower. So this is just going to be a single column or a series in pandas, right? So slight difference there. And then on xvars, what we want to do is use stats models. So equals sm stats models that we imported earlier, to add a constant. And adding a constant is basically an automatic way of adding that column of ones to our data, right? So we don't have to go and figure out like how to add a column of ones or write any code for that. We can just say, hey, add a constant term to this and plug in xvars into that. So this will add that column of ones for us. And then our model over here is going to be statsmodels.ols for ordinary least squares, right? So ordinary least squares is basically what we have been exploring, or the regression model we've been exploring, the one that minimizes the residual sum of squares. It's just called OLS, or ordinary least squares here. You get different types of regressors that are slightly more complicated, like weighted least squares, etc. In this case, we are just using ordinary least squares. And in here, let's specify our y variable, so yvar, and our xvars. And then we are going to say missing equals drop. So we know that there are missing horsepower values, and we'll predict those later. But for now, in stats models, we are just going to get rid of the missing data and not use it for our inferential analysis. This is just a convenient way to get rid of that missing data. And we can specify that this has a constant term in it. So it has const equals true. So that's for the intercept term, or beta naught, when we were discussing the theory. And we want to call .fit on this to fit the model to our values. And then let's go ahead and print a model.summary over here. All right, let's go ahead and run this guy. And this prints out some values from our OLS regression, right? Now, there are a lot of values in this, right? And that might seem overwhelming at first, but I will take you through the ones that I typically consider when looking at a regression model. And in this case, our linear regression model. And yeah, they're like each of these are important information points, but I don't typically use all of them. So it can seem overwhelming at first. And if you do want to look up each of these, they do contribute like different aspects to the analysis, but we're going to stick to the ones that we spoke about in the theory section. Okay, so the first thing that sticks out to me is the R squared value, and this is sitting at 0.6, which means that about 60% of the variance in horsepower can be explained by our model, which simply uses miles per gallon. So I can explain 60% of the variance in the horsepower value by using simply the miles per gallon predictor. Now, adjusted R squared is like a little technical. I'm not going to describe that here, but for our use case and our simple use case, this is going to be very close to our R squared value. So yeah, I'm gonna glean over that for now. Then I will describe the F statistic and probability of the F statistic in a little bit more detail. So I'll get to that in a minute when I describe some of the hypothesis tests happening. But before I do any of that, I'm going to just move on to this section over here where we are looking at the coefficients, right, themselves. So the first one over here is the constant term, so the intercept term. And this is the value for beta naught that we have. And it seems to be 194 over here. Now, this means that if we had a car that had a fuel economy of 0 miles per gallon, it would have a horsepower of 194 horsepower units. Now, this is just a mathematical artifact because a car with a fuel economy of 0 does not exist, right? And if it did exist, I wouldn't recommend driving it, right? And most certainly it would not have a horsepower value of like about 200, right? So that's just one thing I wanted to remark over here in this case. It's just a mathematical artifact in this case. Then the more interesting one is the miles per gallon term over here. So this effectively tells us that for every 1 unit that we gain in miles per gallon, so every 1 mile per gallon that we can travel in our vehicle, we lose about 4 units of horsepower, or 3.8 imperial horsepower units. We lose that. So this is a negative slope, right? And that's just how to interpret this coefficient over here. Now, looking at the standard errors over here, this isn't the residual standard error that we discussed earlier. This is instead the standard error associated with each of the intercepts or the coefficients that we've worked out over here. So on average, the constant coefficient has an error of about 4 units, so it's off by about 4 units on average, and the miles per gallon coefficient is off by about 0.157 units on average. Now, this is a lot bigger over here, and that's probably because the constant value, so where the miles per gallon value is 0, right? We don't have a lot of data there. Like there aren't examples that are very close to 0 miles per gallon. So of course you're going to have a bigger error because you just don't have a lot of data around the point at which this constant occurs. And this is a lot smaller over here because, well, I mean, all the data that we're dealing with is, around the miles per gallon values. Then we have the T statistic over here and the P value over here. So this is quoted as the probability of T being greater than an absolute. Let's go through some of the theory to interpret this and the F statistic. Okay, so a quick overview of the hypothesis testing element of this, just so that we can describe what the P, T, and F statistics are. So these come from the hypothesis tests that are being performed on our model. So Stats Models does this for us. And basically, there are 2 hypotheses, right? There is the null hypothesis, and the null hypothesis basically assumes that one of your coefficients, or the coefficient that you're talking about, the mth coefficient, is equal to 0. And if the coefficient is equal to 0, it means that beta m and the variable associated with beta m has no relationship with the target variable, right? So your mth predictor has no relationship with the target variable. That is the null hypothesis, or the status quo that we're assuming going into this hypothesis test. The alternative hypothesis is that beta m is not 0, and the variable associated with coefficient beta m has a relationship with the target variable. That's what we can kind of project from this hypothesis test. So when you're doing hypothesis testing, and this deserves its own video, right? There are like kind of full courses dedicated to just hypothesis testing, so this is a very high-level description of it. Basically, you assume that the null hypothesis is true. And in assuming that the null hypothesis is true, you then gauge what is the probability of getting the data that I have given the null hypothesis, right? So the p-value is a description of the probability of getting the results that we did under the null hypothesis. That's kind of a very rough explanation of what that means. So if the p-value is very small, it means that it's highly unlikely to occur under the null hypothesis, and thus we can reject the null hypothesis, right? Now, if the p-value is large, it means that your assumption holds true in a lot of cases, and you cannot reject the null hypothesis in that case. Now, the t-value is also interesting because it is the number of standard deviations that your beta value is away from 0, right? And that's interesting to us because our test is whether or not it is 0. So gauging how far away it is useful for us to note. And that contributes or plays into the p-value because a high t-value will lead to a low p-value or low probability of the null hypothesis, right? Or a low probability of getting our data given the null hypothesis. And thus we can say that we can either accept or reject the null hypothesis. Now, I'm very particular in the language that I use, accepting or rejecting the null hypothesis, because I always think about the courtroom example. In a court of law, you are declared not guilty, you are not declared innocent, right? So it's like not guilty and guilty, and that is the hypothesis test in a courtroom. So I'm being very particular about my language. So just looking at this, right, our t-value, let's look at the miles per gallon one, our t-value is negative 24 standard deviations away from 0, meaning that it's pretty damn far away from being 0. And that is why our p-value over here is very, very small. So under the null hypothesis, assuming that the coefficient associated with miles per gallon is 0, it is highly unlikely that we would get this data, right? And so we can reject the null hypothesis and say clearly this is non-zero, right? These values over here, this 0.025 and 0.975 over here, are describing the tails of the distribution, the t-distribution associated with our data, and gives you an idea of the spread of the information. So just looking at this, so this is like the 2.5% marker, and this is the 97.5% marker, giving us a total of 5%. That's like the limit that's typically used in a hypothesis test, about 5%. If something occurs under 5% of the time, you can kind of reject the null hypothesis, etc. But if we look at this, the 0.25% marker is at -4, and our standard deviations are -24 standard deviations away, meaning we are way, way under these limits over here, and that's why the p-value is so small. Now, that is a super quick description of a hypothesis test, and basically you can interpret this by saying that, okay, the p-values are small, so clearly these coefficients aren't 0. And that isn't to say that our estimate is good. That doesn't mean that our estimate is good. We've just tested for whether or not it is 0. We are still yet to judge, or we don't judge in our hypothesis test if this is an accurate estimate. You need to use your R² to kind of guide you there. But we can't say that, because our p-value is small, our estimate of the coefficient must be good. That's not necessarily true. Now, moving on to the F statistic as well, this is kind of related, but this is associated with the hypothesis test, where you are checking if all your coefficients are 0, the null hypothesis, or at least one of them is non-zero. Now, typically, this is for the multiple linear regression case, because you consider not the coefficient, or not the kind of intercept coefficient, right? Or not the constant term. You would take all your predictors coefficients for the F test or the F statistic over here. So this is a little weird for the single variable case, or for simple linear regression. Doesn't really make sense to interpret this, but when we deal with multiple linear regression, this will become more relevant. Right, with that explanation, let us actually go and plot our regression line itself on top of our data. So over here, I'm setting up a matplotlib figure, then putting our typical scatter plot over here, the actual data on top of it. I'm just setting an alpha of 0.6 so that the data is like transparent, so you can see the regression line passing through it. Then creating our linear space over here, or our X domain, like we did in the theory section. adding our constant, and then predicting on top of our x domain over here. So this adds our constant of 1s, and then these are the predictions on top of the full domain. Then we go ahead and plot that as a red line over here and label it as the regression line, then give our axes some nice labels and add a legend so that we have a nice clear graph with labels on it. Let's go ahead and run this. And there is our regression line on top of the miles per gallon data and the horsepower data. So you can see our line going through the data points over here, but as the miles per gallon gets bigger, so our prediction gets worse, right? Because this is kind of curving over here, and it's not really catching at the beginning over here. It's not really catching the points down here. So not truly a linear relationship, but nonetheless, our regression line is not doing too badly. Let's actually plot out the residual values, so the kind of like distances between the known data points and our regression line, so that we can get an idea of what the error looks like in this guy. To get the residuals, it's pretty convenient in the stats models package. We can create a variable, let's call it single var resid equals model.resid over here. So this is taking our model, and the resid attribute contains our residuals in it. So let's just print those out. You basically get an array, model.resid, you basically get an array of the residuals, right, or the residual values. So the distance between the actual data points and our regression model. Let's plot out the distribution of these residuals. Okay, so I've just added a figure over here with a seaborn histo plot, or histogram plot, should I say, and then just created a vertical line over here at the 0 point. That's putting emphasis on it because we want our arrows to be centered at 0. That's one of our critical assumptions for linear regression, right? And then labeling our axes and adding a title. So let's run that. And there's our plot of the residual distribution. This looks pretty normally distributed. There is some skew on the right-hand side because there are like incredibly high values. And I think as we get more and more data points, or if we had more data points, this would probably become worse and worse. But this looks reasonably normal. Let's actually plot the residuals against the predicted values, right? And why I want to do that is because we should see random scatter, right? We assume that the error is random. We should be able to see that inherent randomness. If there is a pattern in it, it means that we have missed something in our model. All right, so this is just some code for a scatter plot again, but this time I'm plotting the fitted values, so the actual y hat values on the x-axis, and then plotting the residuals against those. So let's take a look at that. And this is clearly not random. Our error, as our predicted values get higher, gets worse, and there's a clear pattern to this. So clearly we are missing something in our data, and this is not kind of a random scatter. We are not estimating very well, right? And we kind of knew that already, right? We could see that the pattern was not linear to begin with. We could see that this was kind of more of like an elbow type curve. But what can we do about that, right? So sticking to linear regression, I mean, you could change the model that you're using to have a more complex model. But what I'm going to do is actually scale the miles per gallon variable differently, such that we can get this nonlinear behavior, but keep a linear equation. Effectively, what I'm going to do is feature engineer our predictor. So I'm going to create an entirely new feature based on our predictor variable of miles per gallon. And what I'm going to do then is take cleanDF over here and create a new variable called miles per gallon square root. And this is equal to the square root of our miles per gallon variable. So np.square root cleanDF of mpg over here. And why would I choose the square root? Well, because the pattern that I see over here, just at like a high level, intuiting it, looks like a square root pattern, right? A squared pattern is that parabola kind of shape. And if I invert that, or invert the parabola, I get a square root type pattern. And if I invert my equation, instead of squared, I get a square root. So this is just intuitively the pattern that the data is showing. So let's just add that in as a new feature. So taking the square root of miles per gallon. And then let's go ahead and set up our experiment as usual. So putting a new x variable in our x var set. So now we have miles per gallon and miles per gallon square root over here with our target as horsepower, adding a constant, and then running the stats model's OLS model on top of it. Let's go ahead and run that. And our R squared statistic has improved quite significantly, actually. We now have 73%, or about 73% of the variance is explained by our model. Looking over at our coefficients, we can see our P and T values are still good, meaning that the variable that we have, or variables that we have, clearly have non-zero coefficients, or we can kind of assume that. And then looking at the coefficients themselves, now we have two predictors. So technically we are doing multiple linear regression. Bit of a cheat there, but that's okay, right? Nonetheless, if we look at our coefficients, they now become a little harder to interpret. And this is kind of a critical point when dealing with linear regression and actually models in general. We've gotten better performance, our R squared value is better, but now it's hard for us to interpret the coefficients. If we interpreted our coefficients in the usual way, we would be saying that a single unit of increase in miles per gallon, or along the miles per gallon axis, we would gain 15 units of horsepower. Yet, when we increase the miles per gallon square root by a unit, we lose 191 units of horsepower. So this has become increasingly hard to interpret, right? Because we have added complexity to our model. So we can't just kind of interpret our coefficients in the kind of simple way. And the reason is because our predictors over here are multi-collinear, right? So they share a relationship within in and amongst themselves. And that's clear, right? One is the square root of the other. And this adds complexity to our model, yet made our model more powerful, right? So that is a really critical point. Basically, you get better performance, but you kind of lose that interpretability. Right, so I think this is kind of a natural point to move on to multi-linear regression or multiple linear regression, because we kind of veered off into the territory of dealing with kind of multiple variables anyway. So let's redo our experiment, but this time we are going to use a whole bunch of variables instead of just one or two. So super similar setup to what we had before, but now I'm adding in a whole bunch of the numeric variables over here. So miles per gallon square root, but also weight, cylinders, displacement, and acceleration in here with horsepower as our target variable. Same setup, add a constant, then set up our ordinary least squares model, but this time I'm saving it into a model called multi-model, and then just printing out the summary. So let's go ahead and run this. And this model is way better, right? Because now we can explain like about 90% of the variance in our data with our model. But the thing is, we have added a whole bunch of variables over here, and clearly some of them are collinear. Well, we know about the case where miles per gallon and miles per gallon square root are related because we engineered that. But weight, cylinders, and displacement definitely share a relationship. Intuitively, if I add more cylinders to my engine, I'm going to have more displacement and my car is going to weigh more. That's just the intuition I have about these variables. You'll even notice at the bottom, we now get an error, right? The error saying that the condition number is large. I know we didn't touch so much on the condition number, but this is basically saying that there might be, or that there could be strong multicollinearity in your model. Now, I'm going to use a kind of simpler technique for us to judge whether or not we do have multicollinearity in our model. And that simpler measure for multicollinearity is the variance inflation factor, right? So just to explain that, the VIF is the ratio of variance of beta m when fitting the full model divided by the variance of beta m on its own, or beta m on its own. So it's basically asking how much does the beta m coefficient and the variable associated with beta m contribute to the overall variance of the model, right? And this is the equation over here. Just to remark on some of the notation used in this, this uses r squared xm, where you've got the kind of r squared the r squared coefficient for all of the predictors, or one of the predictors, should I say, the mth predictor in this case, and then the r-squared value of all the predictors except for m. So this minus m can be a bit confusing. It just means not including m, or the set not including m in it. And the rule of thumb for this is that if the variance inflation factor is greater than 10, sometimes it's quoted as 5, between 5 and 10, it is problematic because that means you have inflated the variance, or that coefficient inflates the variance by a factor of 10, right, or more. So we don't have to worry too much about kind of coding up the formula over here. Sci-kit learn actually provides a function for exactly this. You can go and calculate the variance inflation factor using the function provided by sci-kit learn, rather than you having to go and type up a function to do this for you. So that's pretty convenient. Let's go ahead and do exactly that. All right, so I've just set up a empty data frame over here called VIF data. The reason I'm doing this is just to kind of format the results in a table or in a data frame so they look nice, right? And set up a column called variable. This will be the column name, and then the VIF actual value using the variance inflation factor function from sci-kit learn. And this just loops through each of the variables, right? So for each x var in our x vars matrix, grab the values and calculate the variance inflation factor, right? So printing that out over here, we get a table of our different VIF values. Now off the bat, this is huge, right? But this is for the constant. Now we can safely ignore the variance inflation factor for the constant, because of course the constant's VIF is going to be big, because all the variables, every other variable predictor that you're using contributes to the constant value, and thus your VIF is going to be bigger. Now the rest of the variables, however, so barring the constant term, the rest of the variables, however, have huge VIF values, all except for acceleration. Now for miles per gallon and miles per gallon square root, it's clear that these two are related, and of course they have high variance inflation factors, right? Now weight, cylinders, and displacement also have high VIF values because, again, intuitively it seems like these should be related to one another. The only variable that isn't contributing to variance inflation to a great degree is acceleration, right? This is sitting at about 1.6, which is not bad according to our rule of thumb. So what do we do about this, right? What I'm going to suggest is that we go ahead and create a correlation matrix to look at how the variables correlate to one another and the target variable to judge which have the strongest correlations, and then kind of use that to pick which ones we want to keep in our model. So let's go ahead and create a correlation matrix and visualize it. All right, to create a correlation matrix, I'm taking our clean data frame, selecting our features, so the features that we are dealing with and using over here, and then calling .core, and that's for correlation in pandas. So this will create a new data frame which represents the Pearson correlation by default. So Pearson correlation is just linear correlation, which is appropriate since we're dealing with linear regression. Right, but there are other types of correlation that you can look at, like Kendall and Spearman. Those are a little out of scope for this video, but just to note that they do exist there if you wanted to look at other types of correlation. This is just the straight line correlation, and effectively a value of 1 means that the variables are positively correlated, whereas a value of -1 means they're negatively correlated, and anything close to 0 means that there isn't really linear correlation between the variables. Now this is useful for us to explore the relationships in and amongst our predictors. Notice that I have included horsepower as well, so that we can look at the correlation between variables and our target, and then the variables in and amongst themselves. I'm then just plotting this out as a heat map in Seaborn. So the Seaborn heat map is pretty convenient. You can just kind of plug in your correlation matrix over here, annotate it, and then add a color map to it so that values stand out. So like cool to warm, meaning that 1 will be red and like -1 will be like blue, so that you can clearly see these kind of like solid colors appearing. Let's go ahead and print this out. Lastly, just to mention, the format over here just tells you how many decimal points to keep in your printout. We don't want like kind of unending numbers, so I'm keeping this to about 2 decimal points. Let's go ahead and print this. And there is our correlation matrix between all of our variables, predictors, and the target variable over here. Now, we can safely ignore the diagonal because, of course, a variable like miles per gallon is, of course, going to have a perfect linear correlation with itself, right? And equivalently, like weight will have a perfect correlation with weight. So we can kind of ignore this diagonal value. But looking at it in this corner, miles per gallon and miles per gallon square root have a perfect collinear relationship, right? Which is not great for our interpretability of our model. Then similarly, looking at weight, cylinders, and displacement, if we map like weight to, let's say, cylinders, this has a strong collinearity with cylinders as well as with displacement, right? And similarly, like if I go to cylinders, it's related to the other two, displacement is related to the other two. And then even worse, it is also pretty strongly correlated with the miles per gallon and miles per gallon square root values. The only variable that doesn't share collinearity really with the other predictors is the acceleration. Like this has the lowest values, like there is still some collinearity here or correlation happening over here, but the strongest correlation it has, besides with itself, is with horsepower, which is good news because we're trying to predict horsepower. So I think acceleration is a good variable to keep for interpretability, and it has good prediction with it. Now we're going to have to go through and select some other variables or predictors to keep. I'm going to go ahead and keep the miles per gallon square root over here because it has a better correlation with horsepower than just normal miles per gallon does. And from our analysis in the beginning, we could see there's a bit of that curved relationship. So I want to capture that with miles per gallon square root. And then out of weight, cylinders, and displacement, I'm going to go and pick probably cylinders, right? So the reason I want to pick cylinders is because this guy has a strong correlation with horsepower, or strong correlation with horsepower, but it has a weak correlation or weaker correlation with acceleration. And while it does have a strong correlation with miles per gallon square root, it is kind of the lesser of three evils, right? Weight and displacement have very strong correlations over here with miles per gallon square root. So I'm going to pick cylinders out of those three. Let's go ahead and use our picked variables now to create another model and see how it does. So same setup as before. But now I'm picking miles per gallon square root, acceleration, and cylinders as our predictors. And then, of course, horsepower is our target, but similar model to before, right? Very, very similar setup. So let's go ahead and run this. And off the bat, our R squared value has decreased, but it is 0.84, right? So we've lost about like 5-6% in our R squared value over here. But it seems, or we need to observe if our variance inflation factor has improved, meaning that it will be easier to interpret our model. So let's go ahead and inspect the VIF value for this model, or VIF values for this model. So running the VIF code, like calculating the VIFs for this model, we see that, okay, constant is large, but we can safely ignore that. But our other variance inflations are pretty small, right? They're all below 5, as a matter of fact. So this means that we do not have strong multicollinearity, or we can kind of say that, well, by variance inflation, we don't really have multicollinearity in our model. Thus, our model has become more interpretable. We can go ahead, look at our coefficients over here and say that when you increase the miles per gallon square root by 1 unit, you lose 16 horsepower units. When you increase acceleration by 1 unit, so it takes a car a second longer to cover a quarter mile, you lose 4 units or about 5 units of horsepower. And that kind of makes sense, right? Like if a car is slower, you've probably lost some horsepower. And if you increase one cylinder or add a cylinder to the engine, you gain 9 units of horsepower. And that makes intuitive sense as well. Like more cylinders means that your engine is probably more powerful, it can do more work, thus it has a higher horsepower rating. And then just scanning over here to the T and P values, these look pretty good, meaning that none of these are 0, right? And they're pretty far from 0 by the T statistic. The standard errors are pretty small. Again, the coefficient or constant is pretty high in terms of standard error, but that's just because we don't have a lot of data at the 0 marker. And so we have lost a bit of our goodness of fit measure. So we've lost a bit of the R squared kind of rating on our model. But in exchange for that, our model is more interpretable. Now, it does feel wrong, though, to not include the other variables. I mean, clearly they did have relationships with horsepower, right? If I skim across here, they all had relationships with horsepower. So one thing that we can do in terms of linear regression, or keeping in theme with linear regression, there are more complex things that we could do, but sticking to the theme of linear regression, what we can do is add another feature engineering technique over here to model the interactions between two or more of the predictors. So in this case, let's choose something like cylinders and displacement, and let's model their interaction with one another and add that as a variable. So kind of another feature engineering technique that we can use. All right, so adding interactions and feature engineering sounds very fancy. All that I'm going to do is actually create a new variable. Let's call it cylinders or sil x displacement. And this will represent the number of cylinders times the displacement. So it's a new variable that is the multiplication of these two. And to work with that, we're just going to take clean df over here, clean df, take cylinders, and multiply that by clean df displacement. And simple as that, we now have a variable which models the interaction between cylinders and displacement. So let's go ahead and do the typical setup for the model, including cylinders and displacement over here. All right, so same setup as we normally had before, but now we include cylinders x displacement, or cylinders times displacement, and I'm not including cylinders and displacement as variables here. Now, there is kind of a technical principle that applies here called the hierarchical principle. I will add an article on that in the description if you are interested in reading that. It actually describes modeling interactions in a bit more depth, really interesting to see, but I'm not going to go through the exact theory now. However, the hierarchical principle says that you should probably include your variables that you have interactions for, like cylinders and displacement as well. However, I'm going to leave those out for now. I will include them back in later, but I'm going to leave them out for the moment. All right, so running this, we have gained back some of our R squared, right, by including an interaction term. And not quite at that 90% mark yet. We're just shy of that, but we have gained some of our R squared back. And we have our coefficients coming out over here, looking pretty good. They are in fact non-zero. We can kind of reject the null hypotheses over here. Even the F statistic looks good. And if I scroll down, there is the condition number showing up as large. Now, I suspect that this is because of a numerical issue. If you actually look at the coefficient for cylinders times displacement, it is very small compared to the other coefficients, right? So it might be affecting us in that way, just the kind of like scale of the two different variables. However, let's judge multicollinearity by our variance inflation factor to see if we still have multicollinearity amongst these predictors. Right, so let's take a look. And it looks like our VIF values are pretty small, right? So these do not suffer from multicollinearity. Yeah, again, I think that this is large simply because of the scales of the variable. That's something that we actually haven't touched on in this video, is like kind of scaling the variables appropriately. Perhaps reserved for another video, but in this case, I think that's why the numerical error is cropping up. But we did gain back some of our R squared. We don't have multicollinearity, and we can probably interpret our coefficients in the usual way. Right, great. So we've landed on a pretty good model over here. During our inferential analysis, we have studied how the variables relate to one another, and observed how they affect our least squares model, or our linear regression model over here. Now let's move on to the predictive side of modeling, or predictive modeling. So we are going to use a linear regression model to go ahead and predict those missing horsepower values that we had. To start things off on the predictive modeling side, I want to split my data into two. Basically, a set of data where I know the horsepower, and the set of data where I don't know the horsepower, so I can predict on that with the model that we develop, and then use the known data to actually train our model in the first place. So let's go ahead and do that. We'll create two data frames. Let's actually set this to Python. That would help, right? And let's start with without unknowns df over here. And this will equal our clean df from all the way in the beginning, dot drop in a. So we're going to get rid of the unknown values, and the only column that has unknown values happens to be horsepower. So we can go ahead and use that. And let's make this a copy so that they are completely separate. This is just a habit of mine, creating a copy of a data frame rather than operating on the same data frame for the whole time. So let's go ahead and now add our unknowns df. So this one will contain the values that are unknown. Let's call it like with unknowns df. And we'll take our cleaned df and select where clean df horsepower dot is na, so where it is null, and make that a copy as well. Right, with that, now we want to split our data into a training set and a testing set. So for predictive modeling, you want to do some training, right? So fit your model as we have been throughout this video. But you also want to have a set of data where you happen to know the answer, or you know the value of your target variable, but you don't give that to your model such that you can see how well it generalizes to data that it hasn't seen before. And that's kind of a train test split, or a high-level description of why we would do a train test split. So let's do that. I'm going to set up a variable called x over here, and that's just going to be all of our data, but selecting the features that we're interested in, or selecting all of the features that we could potentially use. So I'm going to exclude things like horsepower and car name. Horsepower, because including that in our x values would be cheating, and car name because, well, it's a string and we aren't using it right at all. So we're going to say dot drop over here, dot drop horsepower, as well as car name. And we will put this on axis equal to 1. So what axis 1 means is you're going to drop an entire column rather than dropping rows with these values. You want to drop entire columns. So axis 1 specifies columns in pandas. And then let's set our y value to without unknowns df to the horsepower value. Okay, and now for the train test split, sci-kit learn gives us a really convenient function to do exactly what I described. Basically, select a portion of the data to keep for training and keep another portion of the data for testing. The way to do this is let's grab an x-test set. So x-test, then it's x-train, then x-test, then y-train, so the values that you're reserving for training, and then your values that you're reserving for testing. So x-train, x-test, y-train, y-test is equal to train test split. And we imported this all the way in the beginning, and you feed it your x value and y value. So your x features, your feature matrix or features data frame in this case, and the target values, the y values. And then you specify a test size, so test size in this case. And let's reserve about 20% or 0.2 of our data to keep aside for testing. So 80% will be used for training and 20% will be used for testing. And then because there is randomness involved here, let's just set a seed of random state equals 42. Okay, that should run successfully. Looks good. All right, let's move on to just specifying our features. So the features we actually want to use, it's just convenient for us to keep these. So let's go ahead and specify the features we chose. So that's mpg square root over here. Then we have acceleration, cylinders, or actually we had cylinders x displacement over here. So just these three for now. Now we're going to leverage sci-kit learn for training a linear regression model. And yeah, let's just put that together first, and then we'll kind of look at the statistics like the R squared and stuff. So let's do the training first. So what I want to do is create an xtrain features, which selects our features from the xtrain set. So let's go ahead and take xtrain and select features over here. So just selecting these three for now. And let's create LM for linear model equals linear regression. So this is the sci-kit learn linear regression model. We need to call that over there. We're not going to give it any arguments. We're just keeping things simple. And we do an lm.fit over here. And what we want to fit on is our xtrain features and our ytrain values here. And then just for fun, let's print the intercept and coefficient. So print intercept, and you can get the intercept value from the sci-kit learn API by using something like lm.intercept underscore because it is an attribute of the model. And then print coefficient over here. Similar idea, lm dot co or coefficient. Let's go ahead and run this. And there is our intercept and our coefficients according to scikit-learn on top of the training set that we have. Let's go ahead and calculate the r² value as well as the root mean square error. So I'll touch on that when we reach it, but let's look at both of those values. So what we need is our y-train predictions, so the actual predictions that our model gets, equals lm.predict on top of the x-train feature. So using our model to predict on the training data itself, and then get a train r2 over here for the r² value. And we get this by using lm.score over here, and we will score it with x-train features and y-train over here. So this gives us a r² value. So the score happens to be r². So there you go, coefficient of determination, r2. And now we can use our predicted values to calculate a root mean square error. The root mean square error is just the square root of the square distance between the actual and predicted values. It's a pretty standard metric used when performing kind of this type of machine learning type of exercise, especially when you're predicting values and you have training and testing sets. So let's do RMSE for root mean square error, and we have a scikit-learn function which handles the calculation for us. We just need to give it the true value, so that would be y-train over here, and our predicted values, which is y-train predicted over here. And then we can go ahead and print out these scores. Okay, so let's go ahead and give this a run. And our model is not doing too badly. We have an r² of 0.88, so 88% of the variance in the target variable can be explained by our model. And we have a root mean square error of about 13 units, right? So on average, we miss the true horsepower value by about 13 horsepower units. Now, out of interest, what I'm going to do is actually add in cylinders and displacement, so add them back, and see if that improves our predictive power in both the r² measure and the root mean square error. So let's do this. So cylinder and displacement. Run that. Rerun our training. Ooh, what have I done? Oh, I spelled something wrong. Sorry, it's cylinders. Okay, cool. There's our new intercept and the coefficients. And then let's rerun our training metrics on top of this. And we've gotten slightly better. So our model is more complex by adding these back in, yet our predictive power is greater. Our r² improved to 89%, and our root mean square error dropped to 12.42, which kind of shows that our model may be more complex, but we have more predictive power. So in this case, we are trading our interpretability for more predictive power. Let's go ahead and calculate these metrics on the testing set to see how well our model generalizes. It's all well and good that we've fit our model to the training data and now looked at the predictions on the training data itself. Let's give the testing set to our model data that it's never seen before and see how well it performs in comparison. Okay, so very similar to what we had over here, but now I'm just using the test set as opposed to the training set. So our model has never seen this data before. We are now going to predict on top of it and compare the predictions to the actual values that we know in the testing set. So running that, our r² value is like really close or really similar to that of the training set. And the root mean square error, while slightly worse, is actually really, really close to our root mean square over here. So if this was really high versus the training root mean square error, that means that our model has overfit, or would mean that our model has been overfit and doesn't generalize well to data that it hasn't seen. But we do not see that behavior here. So our model is doing pretty well, actually. Now I want to move on to predicting the unknown values. So the values for which we do not actually know the horsepower to begin with. Like in the testing set, we knew the real values and used it to gauge how well our model was doing. But now I want to predict on values that we have no idea what the horsepower values are. To do this though, we have seen that our model is performing quite well, and what we should do is actually include all our data or train a new model on all of our data. We no longer need to do train test splitting. We did that so that we could see how well our model generalizes, but now we are moving to kind of pure prediction, and we should use all the data available to us to train our model. So I'm going to go ahead and redo the kind of training step over here. So let us actually, yeah, I can type that out from scratch. That's fine. And use that to as our model. So we're going to say LM, so resetting the value of LM again. We're going to set this to linear regression, so a completely new model. But this time we are going to say lm.fit on the whole x set, selecting our features, so all of the x data that we have and all of the y data that we have, right? So this is all of the data for which we know the horsepower values, and we're just selecting the subset of features over here, specifying the target and fitting our model to it. And just for fun, let's print out the coefficient and intercept values. All right, so there is our new intercept and our coefficients using all the data to train a linear regression model. Now let us go and predict on the data for which we don't know the horsepower values. So let's create a new variable called predict unknowns, and this will be lm.predict over here on unknowns_df, or with unknowns_df over here. And we want to select the features that we used. And then let's print out predict unknowns. So over here, we get an array back of horsepower values, right? Or predicted horsepower values. Now this is a little hard to judge because we don't know the car names that it's predicting for. So let's go and take our predict unknowns values and put them into the data frame, like next to the car names, so we can see what the predictions are for, or which cars they're actually for. So to do that, we will take our with unknowns df over here and add a column called horsepower predicted. Horsepower predicted equals predict unknowns. And then we can print out our with unknowns df. So let's go ahead and run that. And yeah, these do not have any horsepower values. These are all NaN values. And if we scroll to the side though, we have our horsepower predicted values over here. All right, so what I'm going to do now is actually take these predicted values and compare them to the values that I can find by looking up these various cars. So I'm gonna go and find the actual horsepower values for these cars and compare what we predicted to this value over here, or the actual value that we can look up. I'm going to go ahead and add that to the README. Okay, so back in the README file, I have added a section called predicted horsepower results over here. And basically, I took each of the unknown cars, like the Ford Pinto, Ford Maverick, the Renault Le Car, that's a pretty funny name, and I have looked up the horsepower values for these and just quoted a source for each of them. I actually came across another dataset called the Vega dataset over here. And the Vega dataset is also an automobile dataset, pretty interesting one, quite extensive, but I did have to look around for the Ford Pinto and the AMC Concorde. And again, the problem with horsepower is that there are so many different types of ways to measure horsepower in different units. So I'm not 100% sure that I've got the right ones, but these are my best guesses. So looking across here, the Ford Pinto prediction is pretty damn close, right? So our predicted horsepower was 74.1, but the actual horsepower is 75. And then the Ford Maverick has a 94.2, and the actual is 82, so a little off. I mean, these are doing okay. The worst performer is on the AMC Concorde over here. I might have looked up the wrong value or found the wrong value. I'm not too sure. But hey, modeling is the art of estimation. These are estimates, and we haven't done too badly. Now, before I close out this video, there was a section that I was in two minds about including, but I thought it was kind of cool. So if you're interested, you can stick around for this. And basically, what I wanted to do was try out an auto feature selector. So in sci-kit Learn, there are automatic feature selection tools, and the one that I've chosen to use is select k-best over here, and then used a regression function along with that to basically look for the best predictors according to this f regression function over here to predict horsepower, right? So in this case over here, this is an auto feature selector. Basically, you throw it a bunch of data and say, hey, pick me this many features that are the best predictors of my target variable, and it will spit out a result. The reason I wanted to do this is because we've done a lot of work to come up with our features, and I wanted to see if it was worthwhile. So basically compare the auto feature selection to our feature selection and see if we did any better. All right, so this basically runs select k-best with the scoring function of f regression. So this is a regressor, and I mean, we are dealing with a regression problem here, or treating it as a regression problem. So that is why I chose that function. And I've chosen k equals 5 because we came up with five different predictors, and I wanted to keep this pretty fair to see if it chose the same 5. And then I'm giving it the training data set to go ahead and get a giving it the training data set to find these values on. Technically speaking, we could just give it the full data set. Let's do that. So let's add that. And then from the result of this, we are going to grab the columns. This just grabs the column indices, and then like using those indices, I get the actual names. It's a little easier than reading the like column integer markers or the integer indexes. So this is just convenience over here. So let's rerun this. Sorry, I'd run this already, but we now have added in extra data. And it seems that this guy has chosen cylinders, displacement, and weight. So it has chosen the same variables as us, except for weight. It traded weight for acceleration, or acceleration for weight, should I say. So let's see if this does well. So I'm going to go ahead and write some code to try this out versus our selected features. Okay, so I've got a feature sets dictionary over here, which has the different feature sets that we're dealing with. I set up a baseline over here with just like miles per gallon square root and acceleration. It's kind of like a baseline model. Then our selected features over here, and then the k-best selected features over here as well. And then I'm just iterating through each of these different feature sets, training up a linear regression model, predicting on that, and testing on it. So I am, using the kind of testing root mean square error as our metric to determine how well our models are doing and compare the models to one another. So let's go ahead and run this. And our baseline model has a root mean square error of about 19 horsepower units. Our selected features have a root mean square error of 12.79 units, and k-best has a root mean square error of 13.92. So for all that work, all that human intuition being applied and like analysis being applied, we gained 1 unit of horsepower on the root mean square error. So on average, our prediction is like 1 unit better than the k-best. Now, in real life, if you're in a pinch for time and need to create a model really quickly, I would suggest using an automatic feature selection technique like k-best or something like that, and then going ahead and doing your analysis. Perhaps even using the auto feature selected model as your baseline model. So yeah, I mean, whether or not it was worth it for all that work and stuff for us to outperform k-best by like 1 unit, well, that's up to you. But I thought that was pretty cool. To round things out and conclude, we learned what linear regression was, both simple and multiple linear regression. We also touched a little bit on polynomial regression when we feature engineered our variables, but that deserves its own discussion. But we learned how to use linear regression practically. Along the way, we also explored nuances between inference and prediction and how we can trade interpretability for more accuracy. And one comment that I wanted to make on something I said in the beginning, I mentioned that one of my clients uses linear regression extensively. Now, I don't want to leave you with the impression that that is simply the best way to do things. I know that there are models that are way better than linear regression. The comment that I wanted to make though was that sometimes it's just more expensive for clients to kind of change the way that they're doing things. So it's not necessarily that linear regression is the best way for them to handle things, but instead it might just be super expensive for them to change how they do things. Anyway, I just wanted to mention that as a caveat. Now, overall, I think that linear regression kind of keeps its place as one of the fundamental models to be used in data science. And if nothing else, it can at least be an educational tool for you to start your data science journey. What do you think about linear regression? I mean, is it a waste of time, or do you think it is truly the ABCs of data science? Let me know in the comments. I'd love to hear from you. Thank you so much for watching. If you found this video valuable, please do consider liking it and subscribing to the channel, or hitting the join button to become a TrentDoesMath channel member. It really helps me out a lot. Before I end this video though, I want to say thank you to my existing subscribers and YouTube channel members. Thank you so much for being patient with me. I haven't published in a super long time, and I wanted to apologize for that. 2025 has started out really stressfully. I had a really stressful contract to deal with and just didn't get around to publishing, but I really missed it, and I'm really humbled by how many people would actually find what I say interesting, and how many people have subscribed to the channel and kind of stayed with the channel as I kind of figured this journey out. So thank you so much. And I am back, so I will see you soon.